Alright, so today we are jumping from segments to our second major piece of the puzzle, angles. These two things make up all of our polygons, segments and angles. So we've looked for the last two sections at segments. Now we're going to look at angles. So first we have to define what an angle is. An angle is formed by two rays that meet at a point. So if we have a point and we have two rays coming out of it, we have an angle. This shape is the angle. So if we could pick that object up and carry it around, kind of like a boomerang, that would be our ray. The hard part is that these these rays on either side do go on infinitely in each direction. A lot of times we don't put the whole ray down. We just put down the segments. We need to know that you can always extend any segment to be the ray. So even when we just draw two segments on the sides meeting at a common point, it is still considered an angle because you can extend those segments out to be rays. The rays are the sides of the angle. The point where they meet is called the vertex. When we name these things, we're going to use a little angle sign in front of the three letters. You have to go from one side to the vertex to the other side. So the vertex is always the middle letter. It doesn't matter which way you go. So we have to be careful when we're conversing with each other to not argue when one of us is using the name BAC for the angle and the other person is using the name CAB for the angle. Are you talking about the same angle? Yes. So we got to know that these are two names for the same angle. And we got to consciously be looking at that and thinking about these things when we're talking about angles and discussing things in class or looking at our homeworks. Sometimes your arguments are because you're just naming them differently. You're both correct. So keep that in mind. Other ways to name angles. We can put a number inside the angle. If the number does not have the degree sign on it, we can call it angle 1. When you have an angle like angle BAC, where there's only one angle there, you can drop the other two and just call it by its vertex. But when you have multiple angles around the same vertex, you cannot call it by just the letter. So if that's letter A, you cannot call any of those angles angle A, because I wouldn't know whether you were talking about angle 1, angle 2, angle 3, or angle 4. If we want the number inside to be the measure of the angle, how many degrees the rays are apart from each other, remember all the way around a circle is 360 degrees. So these angles chop a circle up into a certain number of degrees. When we're looking at how many degrees those two rays are apart from each other, there's a little O in the upper right-hand corner that tells you that this is the number of degrees rather than the number for the name. So anytime it has the degree symbol, it is the measure. Anytime it doesn't, it's the name of the angle. We really want to be able to number our angles to name them, because sometimes we're going to have lots of angles in the same problem. So being able to talk about them easily will be very important to us. Just like in segments, naming things is very, very important. So we got to know how to name things. We got to be able to talk about them correctly. We have a protractor postulate, which is the angle version of the ruler postulate. It tells you to measure your angle. Get a ruler, set it on there, figure out how many degrees the rays are open. So that's what the protractor postulate does. It is the same thing as the ruler postulate, except for angles. We have the absolute value because we want to make sure that when we're subtracting, we get the right positive number of degrees. They are open from each other. 4 big types of angles that you probably already know. Acute angles measure greater than 0 and less than 90 degrees. Right angles measure exactly 90 degrees, and we use the little box to indicate them. Obtuse angles measure greater than 90 degrees and less than 180 degrees. Straight angles measure 180 degrees. These are lines. 1, 2, 3, 4 big types of angles. We are definitely going to use right angles and straight angles a ton. We often chop those angles up into pieces. So sometimes we talk about the acute piece and the obtuse piece, or the acute piece and the other acute piece. We have an angle addition postulate, which is the angle version of the segment addition postulate. So if we take an angle, 2 rays that meet at a vertex, and you have a point that's on the interior of that angle, so in between the 2 rays, and there's a ray drawn coming from the vertex through that point, then the 2 angles that we just formed, their measures can sum together to the measure of the whole thing. So we're talking about measures of angles, and so we haven't written down what that looks like yet. So this will be the first time that we write that down. We're going to need to be able to name all 3 of the angles here. So let's go A, B, C, and D. When we talk about the measure of an angle, there's nothing we can drop. Dropping the angle sign and just putting the 3 letters gets confusing because we use 3 letters for a lot of stuff. And so the notation is a small m in front when you want to talk about the number of degrees associated with how far the rays are apart. So the measure of angle ADB plus the measure of angle BDC is going to equal the measure of the whole angle ADC. So any point on the interior of an angle can have a ray drawn through it from the vertex, which then chops it up into 2 angles. ADB, I highlighted in red there, is 1 angle. BDC in blue is a 2nd angle. And the whole angle that we started with, ADC, I highlighted in green. So the 2 smaller measures add up to the larger measure. It's just as important as the segment addition postulate was. We have to know whether we're working with angles or segments. There is nothing that is more irritating than when you're working with segments and you use the angle addition postulate. You can't use the angle addition postulate with segments. You can't use the segment addition postulate with angles. So be looking at what you have in your givens so that you can figure out what things you need to use. Geometry is a thinking game. You always have to be thinking about what you're writing down. You can't just willy-nilly write stuff down, or you're definitely going to have a hard time. Congruent angles. Just like we had congruent segments, we're going to have congruent angles. If two angles have the same measure, then they are congruent. So if we have two angles, ABC and DEF, and we want them to be congruent, then they have to have the same measure. If two angles are congruent, then they have the same measure. If two angles have the same measure, then they are congruent. If you look at your reason sheet, those are the two if-thens for the definition of congruent angles. We mark those in diagrams with arc-shaped tick marks, which I like to call swoops. They have to have the same number of swoops. So if they're marked congruent, we know a symbol for congruent, which we can still use here. It's going to be our congruent symbol every time we say two things are congruent. So as long as we know their symbols, we put the congruent symbol in between them, and that tells us that the angles are congruent. If two angles are congruent, then they have the same measure. So going to the numbers associated with them, those numbers of degrees are going to be equal. Or vice versa. If you're given the number of degrees of each angle, you can substitute to get the measures are equal, so that then the segments are congruent. Woo! If you need to take a little break now, pause me, take a little break, come back, we'll do the examples, and then you can try some checkpoints and be done. All right, so hopefully you're back from your break and we are continuing on. Name all of the angles shown. So what angles are over there? Angle ABC, angle CBD, and angle ABD. Remember, the order doesn't matter, so if you put angle CBA, these two are the same angle. If you put angle DBC, these two are the same angle. We're not naming new angles, we're naming the same angle just with a different name. So there aren't 6 angles here, there's only 3 angles. We would either use these names or these names, not say, oh, there's 6 angles, here they all are. Example 2. What are you doing down there? If the measure of angle GFJ is 155 degrees, write an equation and solve for x to find the measure of angle GFH and the measure of angle HFJ. Write a reason for each step of the solution of x. Alright, so we look at the picture, we say, okay, we're given both angles and the measure of the big angle. That means we're probably going to use the angle addition postulate. So, the measure of angle GFH plus the measure of angle HFJ equals the measure of the entire big angle GFJ. Angle addition postulate. Substitute. The measure of angle GFH is given over here in the picture. 4x plus 4 degrees. We substitute in, we can drop the degrees. The measure of angle HFJ is 4x minus 1 degrees. And the measure of angle JFJ is 155 degrees. All we did was simple substitution. Replaced each thing with what we knew it was equal to. Now we have to solve. This should seem very familiar from what we were doing before with the segment addition postulate. We're going to combine our like terms. 8x plus 3 equals 155. When we combine our like terms, that's simplifying. Subtraction property of equality. 152. And division property of equality, dividing both sides by 8. 8 goes into 15 once, leaving me with a 7. Put the 2 next to it. 8 goes into 72 9 times. We have x equals 19. They also want us to find the measure of the two angles, GFH and JFH. The measure of angle JFH. We now know that x equals 19, so substituting the 19 in, 4x replaced with 19 plus 4. 4 times 19 is 76, plus 4 is 80. So the measure of angle GFH is 80 degrees. We took the degree sign off. At the end, when we actually write our answer, we have to remember to put the degree sign back in. Measure of angle HFJ. 4x minus 1. So 4 again times 19 minus 1. 19 times 4, again, I get is 76. Subtracting 1 from it, I get 75. The measure of angle HFJ is 75 degrees. We are going to skip down to the very bottom and do checkpoint 5 together. So checkpoint 5 here says if KM bisects angle LKN, and the measure of LKM is 78 degrees, what is the measure of angle MKN? So we have an angle bisector being given here, but we have not yet defined an angle bisector. That could be a problem except for the picture. We have the diagram over here. In the diagram, they labeled the two angles as congruent. So they are giving us in this diagram what the definition of angle bisector is. We can look at the diagram and say, well, from our diagram we know angle LKM is congruent to angle MKN because those are the two angles marked with the swoops. If two angles are congruent, then they have the same measure. This was given in the diagram. If two angles are congruent, then they have the same measure. Means that the measure of angle LKM is equal to the measure of angle MKN. We know the measure of angle MKN right here. I don't remember which one I said. It was supposed to be LKM. So substituting, replacing the measure of LKM with what we know the measure of LKM equals, the 78, keeping everything else the same. The measure of angle MKN is 78 degrees. By substitution. Go back, try your 4 checkpoints, check them at the end, and write down any questions that you may have so that you remember what to ask me tomorrow. And I look forward to seeing you all and talking about angles shortly.